Ladies and gentlemen, dear colleagues, I welcome you on behalf of National Organization Committee at this workshop on distributed parameter systems. We are from Slovak University of Technology, from Institute of Automation, Automation, Measurement and Applied Informatics of Mechanical Engineering Faculty, this university. Dr. Ondrejkovič also is a researcher at Research and Development Center of Železiárne Podbrezová, steel mill from central Slovakia. Our DPS team, Distributed Parameter Systems team, deals with this problems many years. Program of our presentation is here. Introduction, decomposition of dynamics, open loop control, feedback control loops, DPS block set for Simulink, third-party software product of the networks company, interactive control via the internet, control of gravity casting and continuous casting of steel. At present, in control of distributed parameter systems, there are two basic approaches. It is early lumping approach based on discretization of controlled objects. Second is late lumping approach based on results of partial differential equations. Here, presented approach is based on concept of nonlinear lumped input and distributed parameter output system, lumped input, distributed output, nonlinear, acronym NLDS. About motivation. Nowadays, in engineering practice, widely used numerical models for dynamical analysis of technological and production processes. Here, changes of output fields of technological and production processes are analyzed in relation to changes of lumped input, manipulatable input quantities as real NLDS. Based on numerical models of technological and production processes at linear surroundings of given steady-state operation regimes, we can calculate distributed step responses, HHI, a set of such characteristics. Then we can compute distributed impulse responses for discrete convolution model as a linearized model of NLDS in form of discrete lumped input and distributed output system with zero order Horde units. Discrete input, distributed output, zero order Horde units, it is acronym HLDS for this type of representation. Here, the whole output is given as a summation of particular outputs. Here are particular outputs corresponding to individual input quantities. For simplicity, the spatial distribution of HLDS here is considered only on one-dimensional interval 0L here, 0L. But all results are valid also for three-dimensional cases. Here we have some partial causes of ith distributed step response of HLDS. In point xi we have a partial step response. In point xi we have partial response with maximal amplitude in steady state. In steady state, we can introduce reduced profile of step response. Here is a step response in steady state, and to this step response in steady state, we, by this relation, HHR, we introduce reduced profile. This reduced profile in numerator is in steady state step response. In denominator is maximal amplitude, and here by this broken blue line is illustrated reduced profile of this HLDS in steady state, and for n inputs we have a set of such reduced profile as space components of HLDS dynamics in steady state. To partial step response in point xi, we can assign discrete transfer function SHI. It is to ith step response in point xi, and again we have a set of characteristics in time relation to HLDS dynamics. Here, open loop control of HLDS we shall solve in this open control loop from zero initial steady state. CS is a block of space control. CS is block of control synthesis. SS is block of space synthesis, and TS is block of time synthesis. Here are characteristics of dynamics which was here introduced. Time part of HLDS dynamics and space parts of HLDS dynamics for these blocks. Let's now consider distributed step change as distributed reference. Control task here is to find vector of actuating quantities, so that in a new steady state, control error will be minimal in quadratic norm. Control error will be minimal in quadratic norm for actuating vector of actuating quantities in new steady state. First in block SS, yes, here is first block. In block SS we solve we solve the decomposition of distributed reference. Here is distributed reference. Decomposition is solved in this approximation task on the basis functions. These basis functions are here. These these blue broken lines. These basis functions are space components of HLDS dynamics, dynamics. And a solution of this approximation task is vector of optimal approximation parameters with these components. Linear combination of space components multiplied by optimal approximation parameters gives the unique best approximation gives the unique best approximation of distributed reference. Unique best approximation is WO. It is here. And it is with minimal quadratic norm of the deviation. Output of this block of space synthesis is vector of optimal approximation parameters. Here, vector of optimal approximation parameters inputs into block TS, into block time synthesis, where we have single input, single output control loops. Control systems are given as time components of HLDS dynamics. Controllers are designed so that in steady state, in all control loops, control error is 0. Reference quantities are given as components of input vector. These reference quantities are optimal approximation parameters. In control loops, actuating quantities are generated as output of this block. And in this block, actuating quantities on time components of HLDS dynamics generate partial outputs, which partial outputs in steady state are equal to optimal approximation parameters. It is here actuating quantities, time components of dynamics, generated partial outputs. In steady state, partial outputs are equal to optimal approximation parameters. Actuating quantities now input on block HLDS, and through time components of HLDS dynamics, which time components are illustrated by these red blocks, generate partial outputs. Partial outputs in steady state are equal to optimal approximation parameters. It is from this relation partial outputs in steady state are equal to optimal approximation parameters. It is here. Now the whole output is linear combination of space components multiplied by partial outputs. Because of partial outputs are equal to optimal approximation parameters, which is here, partial outputs are equal to optimal approximation parameters, it means that this linear combination is equal to this combination linear with optimal approximation parameters, and it is the unique best approximation of WO of distributed reference, and here then the whole output gives the best approximation of the distributed reference. Consequently, in new steady state, control error is minimal in quadratic norm, and it is solution of our control task. Now in one slide, as summary of control synthesis, here is control loop from zero initial steady state. It means that distributed reference, vector of optimal approximation parameters, vector of actuating quantities, and distributed output are on zero level. When distributed reference inputs on this loop, we have here distributed reference. Control task is now also to find vector of actuating quantities so that in new steady state control error will be minimal in a quadratic norm. First, in block SS, the composition of distributed reference is solved by this approximation task on the set of basis functions. Basis functions are space components of HLDS dynamics. Solution of this approximation problem is vector of optimal approximation parameters. Here are components, and this linear combination with space components gives the unique best approximation of distributed reference Wx infinity. Vector of optimal approximation parameters inputs on TS on block of time synthesis. There are single input, single output control loops. Here control systems are time components of HLDS dynamics. Controllers are designed so that control errors are in all loops are equal to zero. It means that in control process, partial outputs are equal to reference quantities. Reference quantities are components of vector of optimal approximation parameters. Here are optimal approximation parameters. In steady state, when error is equal to zero, partial outputs are equal to optimal approximation parameters. In control loop, actuating quantities are generated, and on the output we have linear combination of space components multiplied by partial outputs. Because partial outputs are equal to optimal approximation parameters, which is here, then this linear combination is equivalent to this linear combination, which is here. It is the unique best approximation, the whole output of distributed reference. It means that the control error in new steady state is minimal in quadratic norm, and so the solution, it is solution of our problem. Finally, we can say that we start at control synthesis from the unique best approximation of distributed reference, and on the output we have the same unique best approximation, and this is finally solution of given control task. Based on introduced blocks SS and TS, we can create also feedback control loops. Here in blocks SS are decomposed distributed reference, distributed output from HLDS block, and in block here are relations, and block TS contains controllers introduced in previous steps. Here are further feedback control loops. merging two SS blocks from previous slide, merging these two blocks, we have this scheme of control problem. When we have measurements in selected points of controlled system, then decomposition of distributed output is solved on the vector level. Further types of control loops based on reduced particular outputs, as it was introduced in first slides. Also based on measurements in selected points are presented on the website dpscontrol.sk in form of extended tutorial and in form of two electronic monographs. Now, in frame of demonstration, Dr. Ondrejkovič will present some possibilities of software support to solution these problems by DPS block set for Simulink, a third-party software product of the Networks company. This product was elaborated in our institute. Then interactive control via the internet from this website. And finally, some results from the area of gravity casting and continuous casting of steel. Please, Dr. Ondrejkovič.
Thank you. Dear colleagues, my name is Karol Ondrejkovič, and I'm from Slovak Technical University, as well as from Železiarne Podbrezová R&D. And I would like to continue with Professor's presentation, but first I would like to tell you something about numerical modeling. I don't know if you are experienced with numerical models, perhaps yes, but nevertheless, usually we have some problem setup that comes from technology, be it gravity casting or continuous casting. And now, the first motivation of creating the numerical model is to reveal some problems that are connected to input parameters. One such problem can be the bad initial temperature field. See, this is the metal that is poured inside the cavity of the casting domain, and here in this region we can see some shrinkage forms. And why is this? It is because the metal is poured from the bad position. It should be poured from this side to compensate for the shrinkage here. Suppose you have only means to compensate for this shrinkage to generate an initial temperature field that has some gradients inside of this casting mode. And now we somehow come to our control problem definition, that we have a technology, we have some problem to be solved, and we have some control inputs to be manipulated. So we remove the casting domain and, we can remove the casting domain. You can see it is empty, and we can, loosely saying, play with the dynamics of the temperature field. And this complex body is the interval 0L that Professor showed you on this picture. So this, in fact, is my casting domain, and these are the temperature fields. So how should we proceed? Actually, in the bottom of the casting domain are the holes. You can see them here, here, here. I will show some better picture and also some copper chills. Once these are driven by electrical power, you can generate such inputs that you minimize the occurrence of the casting defects. I will switch the application to show you. Now this is the control problem setup. It is, in fact, the steel base, like this. And these holes that are not really visible are heated electrically, and these ends are cooled. In this control setup, these holes will be controlled by the control loop that is created in MATLAB Simulink in the product called DPS blockset. So if you have such a model, you can easily generate the transient distributed characteristic that was, sorry, just a moment. Here are my regions, and these are my 4 inputs driven as 1. So these, in fact, if heated, generate some heat flux, and heat flux generates some transient temperature field. And I will get it from the whole domain, or I will get it from the domain that is very important to me, and in this case, it is the bottom of the casting domain. As you can see, it is nothing more than the finite element mesh. And here are the points that are the points of my interest. But it can be also the surface. It can be also the whole body. It depends on the control problem definition. So if I make an input on these 4 holes, I will get the temperature transient. And this temperature transient is this. So this is my casting mode, this is my input, and this is the transient temperature field I will get. And here it may be the point of my interest, or it is the point that reacts very quickly to my input. I will show you how this is simulated in reality. So this is the final stage. You see the temperature field over the casting domain. It's steady. So if you look at this picture, this is the last frame. And the frames before the last frames are unsteady, of course. And we can see the time evolution of the temperature field that is moving like this. And this is recorded into some numerical structure. And once it is steady, I have the temperature field transient for one control input. I can have many control inputs. I can have it here, 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 whenever I want. Now this control input should be, of course, validated against measurements. And this is what we do. So we take this infrared picture, select some point, and we validate the output of my numerical model. So these two should really be the one. I mean, this should be like this, very close. And if it's so, I can work with this transient and create the control loop. And this job is done in MATLAB. So for every manipulating input, I will generate such the transient temperature field, and I will import it into MATLAB. And in MATLAB, I will try to create a control loop that has 5 inputs. Please let me show. So actually, this HLDS is this. This block contains my distributed transients. And this is my job to do in the MATLAB. And this is my reference temperature field I would like to get at the end. And I search for control inputs. Assuming this is true, I will get the best solution. My casting domain, however, reduces only to the bottom. It means I will take only these elements that are at the bottom of the casting cavity, nothing more. So the control loop looks as follows. This is my casting model. This is the room temperature, initial temperature. These are my space synthesis blocks that, that are composed of these components. This is the basis function for one input. And I can see what's going on at the output, what's the required or desired temperature field, and the control loops for each control loop, and the model from the numerical simulation. And here we go. See? This is what I want. This is what I get. These are control inputs. And this tells me how far I am from the output, from the reference temperature field. How much differs this from this surface to this surface. This is the geometric quadratic norm. However, I have limited possibilities to get exactly the temperature field my inputs cannot, of course, generate arbitrary temperature field. It is, in reality, something close to my optimum temperature field I require at the end. So, at the end, I will have some control error, but in technology, it is still perfect solution. So this is the end of the control synthesis solution. This is what I want. This is what I get. These are my electric heaters, control inputs, and this is the error. And how this is made? I will show you the workflow that you also can set up such a control problem. I will take the chair. So let me introduce the DPS block set, the third-party MathForce product. You can easily download it from the web page, dpscontrol.sk from this side. You can download, install into MATLAB and do the same thing as I do. But if I type the DPS, it is for Simulink, so you have to have the license for Simulink. This is the library with the blocks. So here are the container libraries that contain the HLDS block that previously was my casting mode. Also, I have the space synthesis blocks that solves the space approximation problem. I have time control synthesis blocks that are PID, algebraic synthesis, state synthesis, and also robust synthesis. I have quadratic norms that tells me how far I am from my reference variable. This is my display that shows my finite element mesh, my control problem. And this is the source that inputs the reference variable over the finite element mesh, which I get from the some sort of numerical package, be it Procast, be it ANSYS, COMSOL, whatever. I mean, the functionality of the input, of the import of the results is upon the user. So have a look. These are the prepared examples that can be played. We have one-dimensional, two-dimensional, as well as three-dimensional. So one-dimensional problem can be the well-known heated thin metal bore. Yeah. Here we have a thin metal bore that is heated by some electrical heaters at the ends, and the ends are isolated by some kind of thermal insulations. Oh, it's stuck. Okay, it works. Here are the transfer functions, and as well as some solution. But we can see in reality how this works. So we open the model, load the data. The H stands for the transient characteristics that are imported in this model, and the BA are imported in algebraic synthesis block. Once I have it, I can play the solution that looks like this. I want this temperature profile. However, at the initial time is what I get is 0 temperature profile, but the heaters are heating the bar up, and I can see the temperature field rises. At time per 2000, I will switch the reference temperature field to another one, and the temperature field, of course, reacts immediately because heaters also do. The space control task is done in these gray blocks for the output and for the reference variable. And these are actually the inputs for the heaters that are coming to this model. Okay. So this is one-dimensional problem. It can be also something different. I mean, the nature of the problem can be different. It can be also oscillation. It doesn't have to really be a thermal problem only. As you can see, the same problem is applied in the context of different physics. So the physics for the thin metal bar changes to the string that is oscillating, and this is what we actually want, to get the shape of the string like this. And these are our inputs for some piezo actuators. As you can see, the output is shaky. So this is the end of my control problems. This is what I wanted. This is what I could get from my physical problem. As I started with real problem, I mean the three-dimensional, I can also follow. So this is the PID control of the complex shape body. And this body should be heated. And it should be heated to some specific temperature field that is required for the technology for the stamping, for example. So it is some steel metal body defined. The physics is defined here, and the control is defined here. And my space synthesis blocks makes it possible over the whole computational domain. So I load the characteristics, so my physics, my mesh, my elements, and I play the button. And this is what I get. My reference temperature field is constant, about 300 degrees, and I see it is rising up, but not exactly, of course, because I have limited numbers of outputs. In this case, I have four inputs only that act on these small areas that are yellow, and this is the final time. So, in fact, if you have some model in your numerical package, console, you can export the mesh, import into MATLAB. You can also create the dynamics identification based on step responses, and you can set up the control problem using the DPS block set. The thing that should help you is called the DPS wizard. And it provides you step-by-step guidance on your control problem. So let's take the heated metal body again. I will load the data, and I will show you. So this is actually the data you should provide to this. Should come from your numerical environment, your console or ANSYS. And once it's loaded correctly, it is displayed in this figure. If it is displayed correctly, then you can continue. It always asks you for satisfaction. It's very careful. So you have to say, yes, I'm satisfied. And these are, as many characteristics are loaded, so as many inputs you have, and for every input you should provide a sampling period that is only known to you, and of course the amplitudes of step changes that are usually also number one or whatever you prefer. This is how it looks like for the first input. So this is the computation of my first transient characteristic at the input that is located on this boundary domain. If it is done, I will continue with another, the second, the third, that is in the bottom, that is like here. Yeah, this is my third. And the last one forward. These will be the basis of the HLDS block, as well the finite states will be the basis of space synthesis blocks. So if I'm satisfied, these are recorded, and I can show you how this look like. So notice the picture is basically the same, but the amplitude changes. So it is rescaled from 0 to 1, and this is, in fact, this line with the amplitude of 1, scaled down from whatever amplitude it was, scaled down to 1, accordingly to some selected nodes, of course. So I have 4 such outputs: second, third, fourth. Oh yeah. And these are my nodal temperature transients. So I will pick up some specific nodes that are really quick in response to my input, and I will fit them with my transfer function model. And these are also number 4. And this is the identification method for these transients in the time domain. It looks like this. So if the fit is perfect, then your match is fine, and most likely your control problem will also work good for second, third, and the fourth, and you are done. Now it is time to set up the controllers. It can be whatever controller, but in this example, this is PID controller with some time horizon and some control input that is constant temperature field 300, and these are the constants of the controller. As we can see, the D member is 0. We have 4 such simple control loops, and the output of every control loop looks like this. So this is my amplitude, my input, and this is my control error. If I'm satisfied with the control error, I can say yes, I'm satisfied, and I will continue with tuning other 3 control loops. This is the second. Yes, if I'm satisfied, this is third as well as the fourth. These together constitute the control loop that we call is distributed. These are the weight space components of the dynamic. It means that every input has the same weight. All 4 inputs are the same important. And this is actually for inputs, 4 inputs in one action, and this is the control error. If I'm satisfied, I'm done. So this tool will generate my loop. So this is my loop that comes from the process you have seen previously, and you can again run the control problem from the beginning like this, and this is what we get. Actually, you have seen it before. So this is the DPS block set approach in a really nutshell, short description. I just check what I wanted to say more. Oh yeah. So the interactive control problem. So once you have some some outputs generated in your numerical package, you can enter these transients to this web page, and we will deliver the HLDS model, the set of PID controllers, and it is a demonstration of control processes. It doesn't really have to be that complex as in reality. So this is the interactive control service offered from dpscontrol.sk. You have any questions? No. So the time is good. Time is still good, 4 minutes. So if you are interested, I can show you another example for steel industry, or I can perhaps answer.
24 minutes.
34 minutes, no hustle. All right. All right, so as I come from steel industry, I can show you some example on this temperature control in secondary cooling. So
maybe I have a question. Do you use non-linear parameters or generate some non-linearities?
I mean, the question you are asking is the problem is solved, I mean, here. The parameter...
In your summation, I feel like you use simple linear models.
No, these are not, in fact, linear. No. These are nonlinear because the material properties are function of the temperature. I will show you. So actually, this is the steel base I have been showing you before, and you can see that this is a steel, right? And this steel, actually, every parameter, like density, is a function of the temperature. Conductivity is a wild function of the temperature. Of course, we are somewhere here, but it is not linear. It looks linear because I have selected some good points for my control problem, but the complexity of the modeling is in the dedicated environment. The more problem could be caused by the node that is not reacting. I mean, it is the dopravné oneskorenie. Time delay. Yeah, that could really be a problem, but it is a well-known problem in control theory. So the answer to your question, these problems are not linear. So I could move to the last example, that is from steel industry, and it is the continuous casting machine that yeah. So this is actually my control problem domain. It is really big. I mean, this is one man, and this is the casting strand. And here, in this section, this is called the secondary cooling. It is hidden behind this wall, and the secondary cooling constitutes from the series of water jets. And these water jets are generating some temperature profile on the surface of the casting domain. So we can see that some water jet sprays the water towards the surface, and it generates some temperature profile, and these are set, of course, independently. And the goal is to set such water flow rates that the temperature field should go down monophonically, asymptotically. And it leads to the control problem setup, because sometimes you are obliged to change the casting speed velocity that will change the dynamics of the temperature field. So it is, from the point of view of the operator, it is the control disturbance. Yeah, that's the word. So the reason why the temperature field looks like sine wave is the water jet that is discretely distributing along the casting strand. That is, the section is 5 meters long. Let's say we require the temperature field to be changed in some finite time. So this is my time 0 temperature field, and I would like to change it at some time 200 to another temperature field. So this is my reference variable, and this is what I get. It is really slow because the process is really slow. So what I'm really interested about, to have these asymptotic transients or water flow rates and the control error to be minimized. Another problem can be the casting speed change. So my requirement could be the constant temperature field over the casting domain, and I will impose some sudden changes of the casting speed that introduce the disturbance. These are really heavy disturbances, so I cannot diminish them absolutely. And this is what my temperature field looks like in reality. Another control problem is a movement to another operating mode. So every casting speed corresponds to some operating mode of the casting machine. Sometimes I would like to move from one casting speed to another casting speed, and this movement, this transition, should be done as quickly as possible. In reality, this is controlled by open loop. I mean, in reality, we have no feedback on the actual temperature field. We have only the knowledge from the water flow rate relationship to the casting speed relationship. There is no relationship to the actual temperature field because no one really knows. You can know only then when you run the simulations of the temperature field evolution during the casting process. So when there is some simulation, I go back to the beginning of my presentation. When there is some process and you need to know some parameters like temperature field, you make simulations. Once you have the simulations, you can make the control problem if it is required. Thank you for your attention. Any questions regarding technology, MATLAB Simulink, numerical modeling, nonlinearities, or the complexity?
The last example, where was it?
In Podbrezová. It is a Podbrezová steel mill. It is this, I will show you. This is the new casting machine commissioned in 2014 in Podbrezová steel mill. It is a huge investment, and it has 3 casting strands. You can see 2 in operation, but in reality, most of the time they operate all 3 casting strands. And from these, these billets are steel tubes produced. And Podbrezová steel mill is a steel tube producer. This is like this stick, and the exit temperature is about 1000 degrees of Celsius. Any questions?
But it's cooling.
It is cooling, but it is, this is radial. It should be unbended. So these are the unbending sections, and it comes straight. So it should be really hot to be soft to straight. Yeah.
At the beginning, what's the temperature at the beginning?
At the beginning, the casting temperature is about 1560, something like that. It should be melted. This is pouring. It's continuous process. So here it is rapidly cooled, but the steel has very low steel conductivity, so it solidifies only a bit. So it creates some profile that is still liquid inside. So at this place, it is still liquid inside.
If you can go back to the first plant, where was the temperature of,
This?
Maybe this one, yeah, the first.
This is the initial temperature field.
And is it the temperature of the material or of the surrounding around the material?
It is the material. It is the casting strand.
So, and it is in one instant of time.
Yes.
Because it is moving.
Yes.
And if you can go back to this plot, just to understand for me, if the material is moving, so the deviation of temperature is moving with as well?
No. It's Eulerian. It's static. So the casting domain is moving. It's like a river. But you look at the same point always. And if you do not impose the change in some manipulating variable, there is nothing. You are looking in this direction. You are sitting here. This is the bank of the river. This is the bank of the river. And you select some point. And you are observing the point. And there is no change because you are not manipulating the input.
Okay, so if it would be a river, so this hill on the profile is as if there was a stone in the river and the water.
Yes.
Like that,
This is my stone in the water.
Okay.
This is the stone. So I will change the profile of my bottom of the river. There is some stone, and the temperature, the flow changes. So it is Eulerian, not Lagrangian.
Thank you for your attention, for your interest. Other results are on the website at disposal, and now we wish you good appetite for the lunch. Thank you.